there's a river, okay? Oh, I don't know why this isn't moving here. That's great. You take notes on it. So here's the story. Story is you have this river, and let's say Nikki's over here, and let's say Mar is over here. And Nikki has a message that he wants to send Mar, and he is going to call that message M. Okay, so he sends it across the river, but he can't get across the river. There's a little boat person here. We'll call him, I don't know, Bob right here. If he just sends this across with no kind of protection on it, Bob could read the message. He could unroll the, open the envelope up and read the message. Nikki doesn't really want to have that happen, okay? So Nikki puts his message, and I'll start it here, puts the message in a box and puts his lock on it right here. Here's his lock. He puts a lock on that box, and he sends it across the river. And Nikki is the only one with a key to that box. So he sends it across. Bob has to ferry it across the river. And Bob looks at it. He doesn't have a key to the lock. So short of having like an acetylene torch or some sort of like major piece of machinery, can Bob read the message? No, it's locked in the box. It gets over to Mar. The problem now, though, is Mar gets it. Can Mar get inside and read the message? No, Mar can't get it because it's a locked box. She doesn't have the key. Nikki and Mar have not shared keys. They have not shared any information. You get a lockbox. So what Mar does is Mar has her lock on it now. And then she sends it across. Can Bob unlock this box? No, it can't. So Nikki gets it right here. Wait, stop. Shh, my story. Sends it back to Nikki. The message is locked in. Now, what is the only thing Nikki can do at this point?
We can take off his.
Oh, okay. So let's do a little color coding here. Let's take a little color coding here. Okay. So here's Nikki's lock. Here's Nikki's lock. Here's Nikki's lock. So what did Mar add on to it? She added on her lock. So it gets back and Nikki gets it. He can't. The only thing he can really do is do what exactly? He could take off his lock. Okay. So he takes this off right here, and when he sends it across, can Bob read this? No. So when it gets sent across, it arrives over here with just what on it? It just with Mars on it. And what can Mar do with that? The only thing she can do is, well, she can do other things, but she unlocks it, and now she has the message. So we started with M, put it inside the box. Nikki put his lock on it, sent it across the river. Mar added her lock, sent it back. Nikki undid his lock, sent it back across. Mar took off her lock, and the message is read. Why is this pretty neat? What's one reason this is pretty neat, this little story I just told you? What were they able to do and put your surfaces flat on the desk? Every time I have to ask you to do that, I'll give you a 0 for class participation for the day. Yeah, so what's one cool thing about this method of communication? You can repeat things I just said in the story, but what's one cool thing? Bob can't read the message the entire time. What's another cool thing? What? Yeah, you end up being able to send a message securely. Did Nikki and Mar have to talk to each other beforehand? No, they didn't have to share any keys. There's different ways to do this. If I set up keys, like if I give Mar a key to the box, there's a different way to do this. But this is pretty cool because the only thing Mar needs to know is if I get a box that's locked, put my lock on it and send it back to the person who sent it to me. If that's the only thing you know, you can do this as many times as you want with as many people as you want. It's pretty cool. Okay, so what you end up with is, let's change this just a tiny bit. You have a message. Can you convert it to a number if you wanted to? Are there ways to convert messages into numbers? Just say yes. You do that every single day of your life. You did it today when you sent a message via a computer or a cell phone. What does it do? It converts that information into some sort of numeric system and sends those numbers, and then those numbers get read and translated into letters. So could this message be a string of numbers? Yeah. So I could come up with Nikki has his own secret huge number. Let's say that number is P. He multiplies his message times the number P and sends it over to Mar. Mar gets this product of two things. Does Mar really have any idea what that original message is? Ready, everybody? I'm multiplying two 3-digit numbers in my head, and I got this. Do you have any idea what the two numbers are? No. So the message could arrive, and it could be like that. Do you have any idea what the original numbers were? No. Well, how about this? Mar has her own secret number. What letter do you want to call that? Let's say Q. What's Mar going to do? She's going to multiply it in. So she sends it back, and it becomes MPQ. What can Nikki do? he can take away his, he can divide, right? So we can take this out and sends it over here, MQ, and then what can she do? Take out Q and it becomes M. So the locking mechanism becomes multiplication. The locking mechanism becomes multiplication. Is multiplication generally an easy thing to do? Yeah. Yes. Is it something that you can do relatively quickly? Is it something that a computer can do very fast? Yes. Absolutely. So here's a question for you. This is a locking mechanism because you can go one way, but what about the other way? Division would be if you knew what the number was, right? But if I gave you, those are proper words, but if I gave you this number again and said this was the product of two 3-digit numbers, why is that? What am I asking you to do if I said, what are the two numbers that multiply together to get that?
Divide by one of the numbers.
If I asked you to find the two 3-digit numbers that multiply together to get this number, I'm not asking how to do it. What's that process called? We'll see. Factoring. So here's the deal. The first direction we just learned was multiplication. So you take two things and you multiply together to get AB, right? What's the reverse going to be called? No. Factoring. Factoring, factoring, factoring. You end up turning AB into A times B. Which one is easy? Multiplying is easy. Yes, it is done much, much faster. This is easy. It acts as the locking mechanism, not just because it's easy, but because it's a locking mechanism because you can go one way easily, but what? The other way is much, much harder. The other way is much, much harder. So it's really easy. Can you take out your calculator and multiply two 3-digit numbers together really quickly? Absolutely. It takes 2 seconds, right? Everything comes down to this. It is hard to factor. It's hard to factor relative to multiplication. This is really important because this isn't just oversimplification. This is a simplification of the process here, the multiplication of two numbers as a method of encryption. This isn't just a simplification. This is how many messages are coded. Many messages are coded. I've kind of reduced it to something that's easier to understand. But the idea is many messages are encrypted with large number multiplication because going in reverse is really hard without a key. In this case, the key would be like the number you would divide by to get the answer, right? There's other operations like multiplication that are really easy to do one direction, but either really hard or impossible to do in the opposite direction without a key. Why is encryption important?
People can't access data.
They shouldn't, exactly. How many different places in the world? So is there more or less data now than there was last week? Way more. Give you an idea, there's more information in one Sunday issue of the New York Times than the average American saw in their entire life if they lived in the 1700s. There's some statistic like more data is generated every day than in all the days before this day. Like the amount of data being generated is such an exponential function that it's like super steep. You understand what I'm saying? Yeah. The idea is there's lots of data, so people want to protect the data. Is encryption kind of important? Yes. So it's the one method is based on factoring. Okay. We already talked about this right here, but the top line, what does the top line represent? What process does the top line represent? Yeah, distribution, which is a type of what?
Multiplication.
Distribution. Is it an I or no? It's I, right?
Yeah,
it's an I. I don't know. So which is multiplication, right? What does the second line represent? What happened here? What's that called? We just no. Going from this to this. What's that called, everybody? That is factoring. That is factoring. That is factoring. So the idea is we're going to learn different methods over the next week and a half of how to go in reverse. Yeah, you love smaller. So the first thing I need you to remember is, and some people who play sports might have heard this before, take the easy. Have you ever heard this before?
Take the easy way out.
Well, it could be the easy way out, but for example, you might be able to go for the long pass. But generally speaking, are longer passes or shorter passes more higher percentage of success? Which one has a higher shorter passes, right? But is there more glory with like the long bomb? Sure. So one thing you got to tell people. So for example, in Ultimate, I take the easy, which is if someone's open 5 yards away, hit them with that pass. So take the easy in terms of factoring is factor out what you can when you can. So for example, 9z minus 18. What do you think you can pull out of 9z and 18? 9. Generally speaking, you want to pull out the biggest thing you possibly can. Maybe you don't recognize the biggest thing originally. You can take it out in pieces, but take out a 9. It's going to be 9 times what? Minus 2. No, you're not. You got it. Takes practice. Again, takes practice. What about this one? Are there any common factors? Is m in both of those terms? Is p in both of those terms?
No.
So how do you figure this out? What is 35? That's 7 times what? 5. This is really important. This is a great phrase, everybody. I don't think the book uses it. This is called the prime factorization. Why is this called the prime factorization? Those are all prime factors. 7 and 5 are both prime. What about 56? 56 is what? 7 times what? 8. So what can you pull out of both of those? So that's 7 times 8m plus 5p. Exactly. Is there anything else we can pull out? No. So what this is you factor out the greatest common factor. You factor out the greatest common factor. Now, can they get a little bit more complicated? Sure, they can get a little bit more complicated, but they don't get too bad, especially if you're looking for greatest common factors. So, for example, in A here, let's talk about A. What's one thing that they share? What's one factor that these two share? They share 3x squared. Let's say we didn't see x squared. Let's say we just saw 3. If we pulled out a 3, you end up with 3x squared plus 4x cubed. Let's pull out an x. That's going to be 3x times 3x plus 4. Oh, what else can we pull out? We can pull out another what? Another x. So you end up with 3x squared times 3x plus, 3 plus, 3 plus what? Are there any other factors we can pull out? So what would be, if I asked you, what is the greatest common factor of this? What's the GCF? 3x squared. We didn't have to identify it totally at the beginning. Can you do it step by step? Absolutely. Take the easy. You know that 3 is a factor of 9 and 12, so take out 3. Don't sit there obsessing over what's the greatest common factor, what's the greatest common factor. Build it if you need to. It's really easy to make a mistake if you try to jump to the end. We talked about that with word problems, right? If you just try to build a word problem without labeling variables or understanding how you're trying to answer it, what happens? You end up making what kind of mistakes? Really easy, simple mistakes that you shouldn't. So what about this one? What could we pull out of all these first? P. What else could you pull out? Okay, P. We pull out a P. We end up with 32 P to the third minus 24 P squared plus 40 P to the fourth. We pulled out a P, so they all went down by 1. What else could we pull out?
The 8. She said 8.
Someone said P and someone said 8, so I'm going with one at a time. So could we pull out an 8? Yeah. So you get 8P times, not 32, what does it become?
4.
4P cubed minus 3P squared plus 5P to the fourth. Are we done? Nope. What else can we pull out?
4.
P squared. What's the greatest one you can pull out? There's a P squared in each of those, so you end up with 8P to the what? Third, because there's already a P out there. So it becomes 4P what? First, minus 3 plus 5P. Well, we pulled out a P squared, so it just becomes P squared. Is there anything else we can pull out of that? No. So what? We pulled out the 8. So what's the greatest common factor here? What's the GCF? 8P cubed. So could you just start by pulling out 8P cubed if you wanted to? Sure. Do you have to? No. As long as you end up here, you're fine. There's nothing else we can do to that. So again, the process doesn't change no matter what we label this. The process does not change whatever we label. What's one factor that's in all 3 of those? Someone raise their hand and I'll call on you. Yeah, Liv. N what? It's just N, right? Yeah, okay. So if you do N, no, N is, for N, it's the highest power. It would be 24M cubed times what? Just N minus 18M squared plus 6M to the fourth N squared. What else can you pull out? Someone give me something else I can pull out. Summer. 6. So 6n times 4m cubed n minus 3m squared plus m to the 4th n squared. Yep. Someone give me the last thing. Yeah, Milo. M squared, exactly, yeah. So 6m squared n times 4mn minus 3 plus m squared n squared. Is there anything else I can pull out of all of those things? Is there anything else I can pull out? No. So if I asked you, what is the GCF of this? You would say what? 6m squared n. And why did I go m squared n and not nm squared? Alphabetical order, that's it. Just alphabetical order. You just keep on breaking the numbers down until you get 2, 3, 3, and 11. Those are all what? These are all primes. You keep on going until you only get primes, and what do you end up with? The prime factorization. Will you have to do this? Yeah, you'll have to do this. These are good. It feels like you should be able to pull out more, right? It feels like you should, but can you? No, there is no way to pull out any more. You ended up with something like this. Just take a look at this for a sec. If I gave you something that said factor, you have two terms. You have this first term and you have the second term. Is there a common factor that you can factor out? It's in blue. X minus 5. You can take x minus 5 out of both of those products. So if you take x minus 5 out of both of those products, what are you left with? X plus 6 plus 2x plus 5. And then can you clean this up a little bit? Yeah. It's x minus 5 times x plus 6 plus 2x plus 5. What does that turn into, Mar? How many x's do you have right here?
2.
Nope. You have x of them, and you have one of them and two of them. So how many do you have?
You have 3.
3x plus 11. Yeah, 3x plus 11. So this right here factors into that right there. It does factor into that. So sometimes you're going to, it doesn't matter, it could be x minus 5, x minus 12. If it's in both products, you can factor it out. You can factor it out. It can be very useful, but in very specific circumstances. Generally speaking, you're only going to need obs to factor by grouping when I tell you to factor by grouping. So it's not super useful because it's sometimes hard to recognize. But in this case, let's say I asked you to factor this expression right here. Can someone give me one observation they make of that expression? What's one observation? Yeah, Mar, what do you see? Well, they don't all have the same thing, right? You wanted to say they all have something in them, but they don't all. There's nothing you can factor out of all of these, right? But let's say we looked at just these two right here. What's in both of those?
3.
So what could you turn this into? 3 times.
X minus 5.
So now we have 3 times x minus y minus ax plus ay. So another way to say this is 3 times x minus y plus negative ax plus ay, right? I'm just grouping them. This is why it's called grouping. Connor, what's in both of these? What's in both of those? A is in both. If I factor out an a, what do I end up with? 3 times x minus y plus a times what?
X.
Nope.
Negative X.
Negative x plus y. Okay, so we're really close here, aren't we? We're really close. What could I... So this is almost what we have an x minus y here, and we have a negative x plus y there. Can someone tell me what else we could factor out of this? You can factor out, I'll just tell you, you can factor out a negative 1. If you factor out a negative 1, you end up with 3 times x minus y minus a times x what?
Minus y.
X minus y. Correct.
What is switch to
Wait, why
plus y too?
It turns, okay, so if you factor out a negative, listen. If you factor out a negative, this becomes what? If you factor out a negative, that becomes positive. And if you factor out a negative out of this, what does this become? Negative. So that's what happened.
What about the first one?
We didn't touch this one. We left this one alone. All we did was we took out, what did we take out? A negative 1. So what does that a become in front? Negative a. But here's what's cool. What do you see in both of these terms? X minus y. So you end up with x minus y. What goes in front? 3 minus a. We just factored that right there. This one right here is a challenging factoring problem right now. This is called grouping because we factored it in what? Groups. The challenge to this, generally speaking, is that you usually only use grouping when you're told to use grouping. It's super useful in very specific cases. So sometimes, most of the time, if you just try to use grouping by default, it's not going to be a valid option. Grouping will only generally work when I tell you to use grouping, okay? This is not the main method. It needs to be something you understand so that on a test or a quiz, if I say factor by grouping, you could factor by grouping. So if we group this nicely for you, so Connor, tell me what's step one? What should I group? What should I pull out of what?
X squared is 2x.
Oh, look at that. Let's take a look at that. Oh, so what can I factor out of the first group?
X.
So it'd be x plus.
2.
And what do I factor out of the second group?
3.
Ah, x plus.
2.
Ah, bingo. So what do you see in both of those? Yeah, so you end up with x plus 3 times x plus 2. So let's say I gave you another one. Let's say I said x squared plus 7x plus 6. Let's say x squared plus 6x plus x plus 6. Factor that one for me. You factor out of the first group here, this group. What could I factor out there, Emmett?
X.
Yeah, so you end up with x times what?
X plus 6.
Oh, look at that. Do you already have an x plus 6 right here? So can someone tell me what this turns into? What does this factor into, Alex? X plus 1 times x plus 6. Because what's the invisible number right there?
1.
1 is right there. So it's x plus 1 times x plus 6. Yes, it is factors. So what do you do to see if... Yeah, FOIL. X times x is?
X squared minus 5x.
Minus 5x plus 7x minus 35. So this is x squared minus, or plus 2x minus. Is that what we wanted?
Yeah.
It is. Oh, look at that. Okay. So what do you notice? So we said A was what? 7 and B was? So let's look at these numbers here. Let's look at the numbers in our final multiplied form here. Can someone come up with a relationship between those numbers and A and B? What do you notice, Liv? What's the first thing?
-5 and 7 are when they multiply they
Yeah, A times B was equal to what?
equal 35.
Negative 35, right? And what was A plus B?
2.
2. So when you have a coefficient of 1, the key is, what's the coefficient of x squared right there? 1. When the coefficient is 1, you're looking for two numbers that multiply together to get the negative 35 and add together to get 2. So for example, let's say I gave you, I don't know, how about x squared plus 9x, so x squared plus 6x plus 9. You're looking for two numbers, a plus b. What do they add together to be? 6. And what do they multiply together to get? 9. So what does that tell you A is? And B is? And so after you come up with this, you need to test it. So we now think this factors into what? What do we think it factors into? X times X. We think it factors into that, but we need to test it to make sure it works. Because you see these qualifications right here? Are there going to be times when you have more than one possible pair? Yes. Many times you're going to have more than one possible pair. In this case, there's only one, but let's test it. What's x plus 3 times x plus 3? That's going to be x squared plus 3x plus 3x plus 9. And is that x squared plus 6x plus 9? Oh, is that what we wanted it to be? Absolutely. So let's make it a little bit more interesting for you. A little bit more interesting. So let's say we had, what do you know A and B have to add together to be? Negative 5. And what do they multiply together to be? Negative 6. So they add together, oh, it's plus. I'm sorry, it's plus. It's plus. So that's the method you would employ, but now you have to come up with possible pairs. What's one possible pair? A could be what? Can you give me two numbers that add together to get negative 5? Oh, A. So A could be what? And what could B be? Negative 3, is that correct? Because when they do those multiply together to get 6?
Yes.
Do they add together to get negative 5?
Yes.
So what's the next? Are there any other pairs that make that have that be? Is that possible? Any other pairs? What do you think? I don't see any. So what's the next thing you would have to do?
Create the factor.
Test it. Yeah, but create it and then test it. Yes. So you are correct. Yours is a better breakdown. So it would be x minus what?
2.
Times x minus. Test it for me and see if it works.
X plus 2.
Yep.
X plus 6.
Absolutely, that's correct.
That's it.
Okay, so do you feel a little bit pretty comfortable with this? Right now, you are able to factor things that look like this. X squared plus, let's say, Rx plus Q, where R and Q can be any number you want them to be. What does this coefficient at the front have to be? 1. Does everything change if it's not 1? Say yes. Everything changes if it's not 1. There's more to check. It's not super hard, but there's more to check. So when you factor something that's x squared plus something x plus a constant, are you pretty happy? You should be like, oh, that's pretty happy. The one thing you have to watch out for really is this. Let's say I gave you this, x squared plus 13x plus 7. A plus b has to be what? And a times b has to be? Yeah. If you try to find those numbers, what happens? You get a lot of decimals and fractions. We right now are going to be limiting our factorizations to whole integers. So I'll just say integers. Integers. Integers, integers, integers. If you can't factor with just integers, we're going to call it a prime polynomial. The complete answer is this. Is everything factorable?
Yes.
Is everything factorable with integers? No. So, for example, is it possible to factor this? What do you think?
Yeah.
It is. It is possible to factor that. Do you need some non-integers to factor that? Yeah, because when you look at the, oh, a plus b is 13. Oh, what does b equal in this? Well, b is 7 over a, correct?
Yeah.
Okay, so then you take this and you plug it in up there, so you get a plus 7 over a is equal to 13. Multiply everything by a. You get a squared plus 7 equals 13a. Is this something you know how to solve? Not yet. That's called a what? That's a quadratic. Do you know how to solve quadratics yet? No, it's not going to be nice. We get to limit ourselves to nice ones right now, to nice ones.